and we'll keep drifting, floating together through the mysteries. 100 soothing black hole mysteries, looping softly, endlessly through the night. Tonight we'll drift through the edge of event horizons, where time bends and stops, the whisper of Hawking radiation and the quiet pull of singularities, ancient collapses, gentle impossibilities. There's nothing you need to do now. Just let your body sink, heavier, heavier. Feel the mattress holding you, every muscle softening, your heartbeat slowing, thump, thump, matching the rhythm of space itself, shoulders melting down, jaw releasing, each breath pulling you deeper, deeper into the calm, the quiet, the dark. If this helps you rest, tap subscribe and hit like, so others can find this calm too, but only if your eyes are still open. Otherwise, just drift. Now, let's drift into the darkness where black holes wait. Black holes aren't really holes at all. They're places where gravity grew so strong that space itself collapsed inward, folded, compressed, until nothing, not even light, could escape. Imagine a star, massive, ancient, burning for millions of years, and then, one day, it runs out of fuel. The outward pressure stops and gravity wins. The core collapses in less than a second, faster than thought, and a black hole is born. The boundary around a black hole is called the event horizon, not a physical surface, but a point of no return. Cross it, and you're gone, falling forever into the dark. Time itself slows as you approach. From the outside, you'd appear frozen, hovering at the edge, but from your perspective, you'd fall through, peacefully, into the unknown. At the very center, the singularity, where all the mass compresses into a point, infinitely small, infinitely dense, where the laws of physics, as we know them, break down. A place we can describe mathematically, but never truly understand. The closest black hole to Earth sits about 1,000 light years away, a safe distance, nothing to fear, just a quiet companion, invisible, patient, orbiting with a visible star, tugging at it gently, predictably, revealing itself only through its pull. Some black holes spin, rotating hundreds of times per second, dragging space itself around them, like water swirling down a drain. This is called frame dragging, and near a spinning black hole, you couldn't stand still even if you tried. Space itself would carry you along in an endless, gentle orbit. We can't see black holes directly. They emit no light, but we can see what they do to everything around them. When gas falls toward a black hole, it heats up, spiraling inward, glowing brighter and brighter, forming an accretion disk, a flat ring of light, spinning, reaching millions of degrees, bright enough to outshine entire galaxies. Sometimes, jets of energy shoot out from the poles, perpendicular to the disk, streaming out for thousands of light years, powered by the black hole's spin and the magnetic fields twisted around it. These jets can be seen across the universe, beacons in the dark. In 2019, scientists captured the first image of a black hole, not the hole itself, but its shadow, a dark circle surrounded by glowing orange light. The black hole sits in a galaxy called M87, 55 million light-years away, and yet we could see its silhouette. Proof, quiet proof, that these objects are real. The shadow was larger than our entire solar system, 6.5 billion times the mass of our sun, and the light around it, the photon ring, shows us exactly where space curves so much. That light itself is bent into a circle. Gravitational waves, ripples in space-time, were detected for the first time in 2015, caused by two black holes colliding, merging into one. The energy released in that moment was greater than all the stars in the observable universe combined, and yet it passed through Earth, barely a whisper, a tiny stretch and squeeze, measured by instruments so sensitive they could detect a change smaller than an atom. There are stellar black holes, formed from the collapse of massive stars, typically between 5 and 50 times the sun's mass, scattered throughout galaxies, quiet, hidden, waiting. Then there are supermassive black holes, millions, sometimes billions, of times more massive, sitting at the centers of galaxies, including our own, Sagittarius A star, 4 million solar masses, right at the heart of the Milky Way, 26,000 light-years away, anchoring our galaxy, holding it together, a gentle giant, dormant for now. Intermediate black holes may exist too, somewhere between stellar and supermassive, hundreds or thousands of solar masses, harder to find, elusive, perhaps formed from the mergers of smaller black holes, or from the direct collapse of massive gas clouds. We're still searching for them. And then there are the primordial black holes, theoretical, tiny, possibly formed in the first moments after the Big Bang, when the universe was hot, dense, chaotic. Some might be smaller than an atom, others as massive as a mountain. If they exist, they could be the dark matter we've been searching for, invisible, everywhere, holding galaxies together. Micro black holes could theoretically be created in particle colliders, but they would evaporate instantly through Hawking radiation, gone before they could do any harm. A brief flicker, then nothing. Time behaves strangely near a black hole. The closer you get, the slower it moves. If you watch someone fall in from a safe distance, you'd see them slow down, moving slower and slower and slower, their light redshifting, dimming, until they seem to freeze at the event horizon, never quite crossing, but they, from their own perspective, would fall through in moments, experiencing no pause at all. This is called time dilation, predicted by Einstein's general relativity, and it's been measured, proven. Clocks in stronger gravity tick slower, Near a black hole, time nearly stops. If you could orbit close to a black hole just outside the event horizon and then return to Earth, years, decades, centuries might have passed here, while for you, only hours. It's a one-way time machine to the future. Inside the event horizon, the direction toward the singularity becomes as inevitable as moving forward in time. You can no more avoid falling in than you can avoid tomorrow. At the singularity, time and space trade places. What we think of as space becomes time. What we think of time becomes space. A strange inversion beyond our comprehension, where the mathematics break and new physics, unknown physics, must take over. Stephen Hawking discovered something remarkable. Black holes aren't completely black. They emit radiation, very faint, very cold, but real. This happens because of quantum effects near the event horizon. Particle pairs appearing and disappearing. One falls in, the other escapes, and slowly, over unimaginable timescales, the black hole loses mass, evaporates. A black hole the mass of the Sun would take 10 to the 67th power years to evaporate, far longer than the current age of the universe, but smaller black holes evaporate faster, and in their final moments they would explode, releasing all their remaining energy at once, a quiet end to an invisible giant. The radiation is named after Hawking, but it represents something deeper, a connection between gravity, quantum mechanics, and thermodynamics. Black holes have temperature and entropy. They follow the laws of physics, even as they challenge them. The temperature of a black hole is inversely proportional to its mass. The bigger it is, the colder. Supermassive black holes are nearly absolute zero, colder than the cosmic microwave background. So they actually absorb more radiation than they emit, growing very slowly over time. But in the far future, trillions of years from now, when the universe has expanded and cooled, even supermassive black holes will begin to evaporate, shrinking, warming, until they too disappear, leaving nothing behind but a whisper of radiation scattered across the void. If you fell into a black hole, feet first, the gravity at your feet would be stronger than at your head, pulling you apart, stretching you. This is called spaghettification, a gentle word for a violent process. But for a supermassive black hole, the event horizon is so large, the tidal force is so gentle, you might not even notice crossing it. You'd pass through, peacefully, looking back. You'd see the universe speeding up, stars being born and dying, galaxies colliding, time itself racing forward ahead of you, the singularity behind you, everything you've ever known, redshifted, dimming, disappearing. No one knows what happens at the singularity. Our equations fail. Space and time lose meaning. Perhaps you'd be crushed to a point. Perhaps you'd pass through to another universe. Perhaps something stranger still. we can only imagine. Some physicists think black holes might be connected through wormholes, Einstein-Rosen bridges, tunnels through space-time, linking one black hole to another or to a white hole, spewing matter out somewhere else. But no one has ever seen a white hole. And the wormholes, if they exist, would be unstable, collapsing too quickly for anything to pass through. The information paradox asks what happens to information that falls into a black hole. Does it disappear forever, or is it preserved somehow, encoded in the Hawking radiation, or on the event horizon itself? The holographic principle suggests that all the information inside a black hole could be stored on its surface, like a two-dimensional projection of a three-dimensional reality. Nearly every large galaxy has a supermassive black hole at its center. They seem to grow together, the black hole and the galaxy, feeding each other, shaping each other. When galaxies collide, their central black holes eventually merge, orbiting each other for millions of years, spiraling closer and closer until finally they touch and become one, releasing gravitational waves that ripple across the universe. Quasars, the brightest objects in the universe, are powered by supermassive black holes, feeding on vast amounts of gas and dust, the accretion disk glowing so bright it can be seen billions of light years away, outshining 1 trillion stars. Active galactic nuclei, AGN, are galaxies with black holes actively feeding, their jets shooting out, lighting up the cosmos. But most black holes, including our own, are quiet now, starved of fuel, dormant, waiting. The black hole at the center of the Milky Way, Sagittarius A star, occasionally flares when a star or gas cloud wanders too close. The material heats up, glows, and then fades, a brief moment of activity in an otherwise calm existence. We orbit this black hole, our sun, our planet, our solar system, circling once every 230 million years, a galactic year. We're about halfway through our current orbit, safe, stable, held in place by the gravity of stars and dark matter and the black hole itself. Some scientists think black holes could be doorways to other universes or other times, that inside the event horizon, the rules change and reality, as we know it, ends. Rotating black holes, Kerr black holes, have 2 event horizons, an outer one and an inner one, and between them, a region called the ergosphere, where space itself is dragged around the black hole, faster than light. In this region, you could extract energy from the black hole by dropping something in and catching what comes out, a Penrose process, named after physicist Roger Penrose, a way to harvest energy from rotation itself. Charged black holes, Reissner-Nordstrom black holes, also have 2 horizons, but they're unlikely to exist in nature because black holes would quickly neutralize any charge by attracting opposite charges from space. Naked singularities, singularities without event horizons, are prohibited by the cosmic censorship hypothesis, the idea that the universe protects us from the mathematical chaos of singularities by always wrapping them in event horizons, hiding them from view. But whether this is truly a law or just a tendency, no one knows. Black hole bombs, theoretical constructs where you place a mirror around a rotating black hole, trapping its Hawking radiation. The radiation bounces back and forth, amplifying until the black hole explodes, releasing all its energy at once, a weapon or a power source, depending on your perspective. Cygnus X1, the first black hole ever discovered and found in 1971 in the constellation Cygnus, about 6,000 light-years away, orbiting a blue supergiant star, pulling gas from it. The gas heats up, emits X-rays. That's how we found it, watching the invisible through what it does to the visible. V404 Cygni, another black hole in Cygnus, periodically flares into brightness as it devours material from its companion star. In 2015, it had a major outburst, visible to amateur telescopes, a black hole seen from Earth through the light of its feeding. M87 star, the first black hole ever photographed, 6.5 billion solar masses in the galaxy Messier 87, 55 million light-years away. Its jet stretches 5,000 light-years, a stream of particles moving near light speed, lighting up intergalactic space. TON 618, one of the most massive black holes known, 66 billion solar masses, powering a quasar so bright it's visible from Earth, 10 billion light-years away, formed when the universe was very young. How it grew so large, so quickly, remains a mystery. Phoenix A, the black hole at the center of the Phoenix cluster, estimated at 100 billion solar masses, perhaps the largest known, though measurements are uncertain. It sits in a galaxy cluster, 5.7 billion light-years away, quietly, impossibly massive. In the distant future, long after the last star has died, black holes will be the only objects left, drifting through a cold, dark, expanding universe. They'll orbit each other, slowly, losing energy to gravitational waves, spiraling inward over trillions of years, eventually merging, forming larger and larger black holes, forming larger and larger black holes, and then even those will evaporate through Hawking radiation, shrinking over timescales so long we can't comprehend them. 10 to the 100th power years, a Google years, and finally a flash, and they're gone. The universe will be empty then, just photons, stretched by expansion, cold, dark, silent, no stars, no planets, no black holes, just the ghost of what once was. But perhaps, in that far future, quantum fluctuations could create new universes, baby universes, budding off, each with their own laws of physics, and perhaps, in one of them, Black holes will form again, stars will shine, and somewhere, someone will fall asleep thinking about the mysteries of darkness and light and time. Light, the fastest thing in the universe, travels at 209,792,458 meters per second. Nothing can go faster, and yet, near a black hole, even light bends. Gravitational lensing. When light from a distant star passes near a black hole, the black hole's gravity bends it, curves it, focuses it like a lens. We can see multiple images of the same star, or rings of light, Einstein rings, named after the man who predicted them. The photon sphere, a region just outside the event horizon where light can orbit the black hole, traveling in circles, forever, trapped but not fallen in. If you stood at the photon sphere, you could see the back of your own head, light from you, traveling around the black hole and back. Inside the event horizon, even if you pointed a flashlight outward, the light would curve back down, falling toward the singularity. There is no escape, not for matter, not for light, not for information. Redshift, the stretching of light, happens as light climbs out of a gravitational well, losing energy, shifting toward red. Light from near a black hole is severely redshifted. By the time it reaches us, it's dimmer, cooler, older. Blue shift, the opposite, happens when light falls into a gravitational well, gaining energy, shifting toward blue as you fell toward a black hole. The light ahead of you would blue shift, growing brighter, more energetic, until it might even become lethal. Gamma rays, X-rays, bathing you in radiation. Gravitational redshift was one of the first tests of general relativity, measured in 1959 in a tower at Harvard. Light traveling up lost energy, just as Einstein predicted, and near a black hole. The effect is millions of times stronger. The Schwarzschild radius defines the size of the event horizon. For a non-rotating black hole, it's proportional to the mass. Compress the Earth to the size of a marble, and it becomes a black hole. Compress the Sun to less than 6 kilometers, and it too would collapse. The formula is simple. R equals 2 gm over c squared, where g is the gravitational constant, m is the mass, and c is the speed of light. Elegant, precise, describing the boundary of the unknowable. The Kerr metric describes rotating black holes, much more complex but more realistic, because everything in the universe rotates. Stars rotate, planets rotate, and when they collapse, that rotation doesn't disappear. It concentrates, intensifies. The No-Hair theorem states that black holes are remarkably simple. They are defined by only 3 properties: mass, charge, and angular momentum. Nothing else matters. Whether the black hole formed from hydrogen or iron, from stars or gas clouds, the result is the same. A black hole has no hair, no distinguishing features, just these 3 numbers. The Bekenstein-Hawking entropy formula, S equals kc cubed A over 4gh bar, relates the entropy of a black hole to its surface area, not its volume. This was shocking when first discovered. Entropy, a measure of disorder, information, is stored on the surface, suggesting our three-dimensional universe might be a projection of information encoded on a two-dimensional boundary. Penrose diagrams map the entire space-time around a black hole onto a finite diagram showing past, present, future, event horizons, singularities, the entire causal structure. Light always travels at 45-degree angles, and you can see, visually, what can reach what's connected to what. Geodesics. The paths objects follow in curved space-time near a black hole. These paths spiral inward inexorably, inevitably. Once past the event horizon, all geodesics lead to the singularity. There are no paths out. Sometimes black holes come in pairs, orbiting each other, bound by gravity. Two dancers, spiraling slowly inward. Binary black holes form in several ways. Two massive stars orbiting each other, both collapse, both become black holes, and they continue their dance. Closer now, faster, or galaxies merge, and their central black holes, after millions of years, find each other and begin their final approach. The orbital decay is slow at first, losing energy to gravitational waves, ripples in space-time, carrying momentum away. The black holes spiral closer, imperceptibly, for eons. But as they get closer, the waves grow stronger, the orbit speeds up, and in the final moments, they're orbiting hundreds of times per second, moving at a significant fraction of light speed, space itself shaking with their motion. The merger, when they finally touch, lasts less than a second, the two event horizons becoming one, the singularities merging, releasing more energy in that instant than all the stars in the visible universe combined, but not as light, as gravitational waves, invisible, passing through everything. The ring down, after the merger, the new black hole vibrates like a bell that's been struck, ringing at specific frequencies determined by its mass and spin. The vibrations decay quickly, settling into stillness. A new black hole, slightly larger than the sum of its parts, because some mass converted to energy radiated away as gravitational waves. GW 1F914, the first gravitational wave detection that came from two black holes merging, 1.3 billion light-years away, 36 and 29 solar masses, becoming 62 solar masses, 3 solar masses, converted entirely to energy in less than a second. And we felt it here, on Earth, a tiny squeeze and stretch, but we felt it. Since then, dozens more have been detected, each one unique, each one teaching us something new about how black holes form, evolve, merge, about the universe itself. Accretion disk coronae, hot regions above and below the accretion disk, where temperatures reach billions of degrees, emitting X-rays, gamma rays, visible across the universe. quasi-periodic oscillations, QPOs, flickering in the X-ray light from black holes, repeating patterns like a heartbeat caused by clumps of matter in the accretion disk or by oscillations in the disk itself. The frequencies tell us about the black hole's mass and spin, relativistic jets, streams of particles shot out from near the black hole's poles, travelling at 99.99% the speed of light, stretching for thousands, even millions of light years. How they form exactly is still debated, but they involve twisted magnetic fields and the black hole's rotation, channeling energy outward with incredible precision. Jet precession, when the jet wobbles like a spinning top sweeping across the sky, creating spiral patterns or changing which direction we see it from Earth. Tidal disruption events, when a star wanders too close to a black hole. The tidal forces rip it apart, spaghettifying it. Half the star's material falls into the black hole, creating a bright flare. The other half is flung outward, escaping at high speed. These events are rare, but spectacular when they happen. Hypervelocity stars, stars moving faster than escape velocity from the galaxy. Some may have been flung out by close encounters with the supermassive black hole at the galactic center, or by binary interactions where one star fell in and the other was ejected, shooting out into intergalactic space. Hill's mechanism, a process where a binary star system approaches a black hole. One star is captured, the other is ejected at incredible speed, while the black hole gains a new companion, perhaps explaining some hypervelocity stars and some of the stars in tight orbits around Sagittarius A star. Black holes captured the public imagination long before we had proof they existed. They appear in science fiction, films, books. Interstellar, the 2014 film, featured Gargantua, a supermassive black hole, rendered with scientific accuracy, using equations from general relativity. The accretion disk appeared above and below the black hole because light was bent around it. Gravitational lensing, visualized beautifully. The film explored time dilation. 1 hour on a planet near the black hole equaled 7 years on Earth, an extreme example, but based on real physics, showing how time is flexible, malleable, near such intense gravity. Event Horizon, a 1997 horror film, imagined a ship that created an artificial black hole for faster-than-light travel, but instead opened a gateway to somewhere dark, somewhere wrong, using black holes as portals, a common science fiction trope, a brief history of time. Stephen Hawking's book brought black holes to millions of readers, explaining complex physics in accessible language, inspiring a generation to look up, to wonder, to question. Black holes appear in Star Trek, Doctor Who, Stargate, usually as dangers, obstacles, or plot devices, but occasionally as sources of power or gateways to other times and places. They represent the ultimate unknown, the ultimate mystery, and so they resonate with us. We fear them, we're drawn to them, we imagine what lies inside, even knowing we can never truly know. The Event Horizon Telescope, EHT, isn't a single telescope. It's a network, radio dishes around the world, working together, synchronized by atomic clocks, creating a virtual telescope the size of Earth itself. They observe at 1.3 millimeter wavelength, because this wavelength can penetrate the gas and dust around black holes and is sensitive to the emission from hot plasma in the accretion disk. The data is enormous, petabytes of information, too much to transmit over the internet, so it's recorded on hard drives, physically shipped to a central facility, and then correlated, combined, processed, turning raw data into an image. The imaging process takes months, using sophisticated algorithms to reconstruct what the black hole looks like from the patterns of radio waves detected around the globe. LIGO, the Laser Interferometer Gravitational Wave Observatory, detects gravitational waves using two L-shaped detectors, each arm 4 kilometers long. Lasers bounce back and forth, measuring distances to within a fraction of a proton's width. When a gravitational wave passes through, space itself stretches and squeezes. One arm gets slightly longer, the other slightly shorter, and LIGO detects this change, confirming the wave and revealing the source. Virgo, another detector in Italy, works with LIGO. 3 detectors together can triangulate the source of the waves, pinpointing where in the sky the merger occurred. X-ray telescopes, like Chandra and XMM Newton, observe the hot gas around black holes, seeing through dust and distance, mapping the high-energy universe. Radio telescopes, like the VLA, the Very Large Array in New Mexico, detect radio emission from jets and accretion disks, building maps of black hole systems. Together, these observatories are revealing black holes in more detail than ever before. We're in a golden age of black hole astronomy, seeing the invisible, hearing the silent, understanding the incomprehensible. The black hole information paradox, one of the deepest mysteries in physics, asks a simple question: what happens to information that falls into a black hole? In quantum mechanics, information is never destroyed. It can be scrambled, hidden, transformed, but never lost. This is called unitarity. But in general relativity, anything that crosses the event horizon is gone forever, crushed at the singularity, erased from the universe. These two theories, our best theories, contradict each other. Hawking initially argued that information is destroyed, that black holes violate quantum mechanics. This shocked the physics community. But later, he changed his mind, suggesting that information might be encoded in the Hawking radiation, subtly, in correlations between particles, too complex to decode, but present. The holographic principle proposes that all the information inside a black hole is encoded on its surface, the event horizon itself, like a hologram storing three-dimensional information on a two-dimensional surface. This led to a radical idea that our entire universe might work this way, that we and everything we see might be projections of information encoded on a distant boundary. The firewall paradox suggests that if information is preserved, then the event horizon might not be smooth, but instead be a wall of high-energy particles, a firewall that would incinerate anything crossing it, contradicting the idea that you could fall through peacefully. Some physicists propose that black holes don't have interiors at all, that they're fuzzballs or gravastars, exotic objects that avoid singularities and preserve information naturally. Others suggest that black holes are connected to quantum entanglement, that ER equals EPR, Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs, wormholes equal entanglement, a deep connection between space-time geometry and quantum information. The paradox remains unsolved, driving research at the intersection of quantum mechanics, gravity, and information theory. Perhaps its resolution will lead to a theory of quantum gravity, the holy grail of physics. At the quantum level, black holes become even stranger. The singularity, where our equations break, is where quantum gravity should emerge. String theory proposes that black holes are made of strings, tiny vibrating filaments wound up in complex configurations. The entropy, the information content, comes from counting these configurations. Loop quantum gravity suggests that space itself is quantized, made of discrete chunks, and at the center of a black hole, instead of a singularity, there might be a quantum bounce, matter compressing, then rebounding, possibly creating a white hole in another universe. Black hole complementarity is a principle that tries to resolve paradoxes. It says that different observers see different things. An outside observer sees information encoded on the horizon. An infalling observer passes through smoothly. Both descriptions are valid, but they can never compare notes. Quantum entanglement near black holes creates the firewall paradox. If particles are entangled with Hawking radiation, and also with particles inside the horizon, this violates the rules of entanglement. Something has to give. Either the horizon isn't smooth, or information is lost, or our understanding is incomplete. Some theories propose that black holes have soft hair, not literally, but metaphorically, quantum information stored in subtle quantum states at the event horizon that could encode information about what fell in. The fuzzball proposal replaces the event horizon and singularity with a fuzzy quantum object that fills the entire region. No interior, no singularity, just a dense tangle of strings that looks like a black hole from far away. Virtual particles near the event horizon constantly pop in and out of existence. quantum fluctuations of the vacuum, and these fluctuations are what create Hawking radiation. One particle escapes, the other falls in, and slowly the black hole shrinks. Between stellar black holes and supermassive ones, there should be intermediate mass black holes, hundreds to thousands of solar masses, but they're elusive. We've found hints, ultraluminous X-ray sources in nearby galaxies, shining too bright to be stellar black holes, but not quite bright enough to be supermassive. Some globular clusters, dense collections of old stars, may harbor intermediate mass black holes at their centers, holding the cluster together, their gravity keeping stars in orbit. But proving they exist is difficult. They don't feed like supermassive black holes. They're not as common as stellar black holes. They occupy a middle ground, hard to observe, hard to confirm. One candidate, HLX-1 in the galaxy ESO 24349, flares periodically, suggesting a black hole of about 20,000 solar masses, feeding on a companion star. Another, in the dwarf galaxy NGC 4395, has a black hole estimated at 10,000 to 100,000 solar masses, much smaller than typical supermassive black holes, possibly representing an intermediate stage. Gravitational wave detections have found black holes around 100 solar masses, larger than expected for stellar black holes, possibly the lower end of intermediate mass, or the upper end of stellar. The boundary is blurry. These objects could be the seeds that grow into supermassive black holes, or they could form from collisions in dense star clusters, black holes merging repeatedly, building up mass over time. Understanding intermediate mass black holes helps us understand the full population, how black holes form across all scales, and how they grow from stellar remnants to galactic giants. Black holes can spin, some slowly, some incredibly fast, up to 99.9% of the theoretical maximum. Spin is measured by the dimensionless parameter A, ranging from 0 for non-rotating to 1 for maximally rotating. Most observed black holes have a between 0.5 and 1. The spin of a black hole affects the space around it. A spinning black hole drags space in the direction of rotation, frame dragging, the lens-thirring effect. Near a rapidly spinning black hole, the innermost stable circular orbit moves closer to the event horizon. Matter can orbit closer, get hotter, shine brighter before falling in. The spin also affects the jets. Rapidly spinning black holes produce more powerful jets, extracting rotational energy and converting it to outward motion. When two black holes merge, their spins can be aligned or misaligned. Aligned spins produce more gravitational waves. Misaligned spins create a wobble that shows up in the signal. Black holes can spin up by accreting matter from a disk rotating in one direction, gradually adding angular momentum, or they can spin down by accreting matter chaotically from random directions, or by merging with another black hole, spinning the opposite way. The spin history of a black hole tells the story of its formation and its interactions with other objects over billions of years. Some supermassive black holes spin near their maximum rate, suggesting they grew mostly from smooth accretion. Others spin slowly, suggesting chaotic growth or recent mergers. Measuring spin requires precision. Looking at the X-ray spectrum, the shape of emission lines, the behavior of matter near the event horizon, it's technically challenging but incredibly revealing. What if a singularity existed without an event horizon? A naked singularity exposed to the universe? Roger Penrose proposed the cosmic censorship hypothesis, that the universe protects us from naked singularities, that every singularity must be hidden behind an event horizon. But is this always true? Or could there be exceptions? If you spin a black hole fast enough or charge it sufficiently, the event horizon might disappear, leaving the singularity exposed. But in practice, spinning up a black hole has limits. Before you reach the critical spin, other processes intervene, preventing it from going further. Charged black holes face similar limits. The universe provides charge neutralization. Particles of opposite charge are attracted, fall in, and balance the charge. So naked singularities remain theoretical, mathematical curiosities that probably don't exist in nature. But if one did exist, causality could break down. Signals could emerge from the singularity without passing through an event horizon, violating our notions of predictability. Traveling near a naked singularity could allow closed time-like curves, time travel to the past with all the paradoxes that entails. The cosmic censorship hypothesis protects us from this chaos, ensuring that singularity remain hidden, safely tucked away where they can't interfere with the rest of the universe. Most physicists believe cosmic censorship holds, but proving it rigorously remains an open problem in general relativity. Spacecraft use gravitational assists to gain speed by passing close to planets, stealing a tiny bit of their orbital energy. But near a black hole, the effect is far more extreme. The Penrose process allows you to extract energy from a rotating black hole by dropping an object into the ergosphere, splitting it into two pieces. One falls in, decreasing the black hole's rotation. The other escapes, with more energy than the original. This could theoretically power civilizations advanced enough to harness it, extracting rotational energy from a spinning black hole until it stops rotating entirely. Gravitational slingshots near black holes could accelerate spacecraft to relativistic speeds, a significant fraction of light speed in a single pass. But the tidal forces would be enormous. Only near supermassive black holes, where the horizon is large and tidal forces gentler, could this be remotely safe. Hyperbolic orbits that swing close and then away, could redirect a spacecraft, dramatically changing its trajectory with minimal fuel expenditure. Of course, this is entirely theoretical. We have no technology to travel to black holes or survive the journey, but the physics is sound, and perhaps someday, far in the future, advanced civilizations will use black holes not as dangers to avoid, but as tools, engines, gravitational highways through the cosmos. If black holes are regions where nothing escapes, could there be the opposite? White holes where nothing can enter? Mathematically, white holes are allowed. By the equations of general relativity, the time-reversed solution to a black hole. Instead of matter falling in, matter would explode outward from a singularity into the universe. But white holes are unstable and have never been observed. They likely don't exist in nature. Some theories propose that the Big Bang itself was a white hole, the ultimate ejection of matter from a singularity, creating space, time, everything. Or that the other side of a black hole might connect to a white hole in another universe, a wormhole linking the two. When you fall into a black hole, you'd emerge from a white hole, somewhere else, someone else. But the connection would be unstable, collapsing almost instantly, closing the door behind you. White holes are fascinating as thought experiments, as mathematical curiosities, but as real objects, the universe seems not to make them. They violate thermodynamics. Entropy should increase, but a white hole, spontaneously ejecting matter, decreases entropy locally. Perhaps quantum effects prevent their formation, or perhaps they existed briefly in the early universe and decayed away. For now, they remain ghosts in the equations, shadows of black holes, interesting but absent. When a black hole feeds, radiation pressure pushes outward from the hot accretion disk, while gravity pulls inward. There's a balance point, the Eddington limit, where radiation pressure equals gravitational pull. Beyond this limit, the black hole can't accrete faster. The radiation blows away the infalling material, creating a natural speed limit on growth. For a solar mass black hole, the Eddington luminosity is about 10 to the 31 watts. Enormous, but finite. For supermassive black holes, it's proportionally larger, allowing them to shine brighter than entire galaxies. But some objects exceed the Eddington limit. Super Eddington accretion shouldn't be possible, yet we observe it. Ultra-luminous X-ray sources shine too bright for their estimated masses, suggesting either they're more massive than we think, or they're accreting super Eddington. Beaming might explain it, if the emission is directional, collimated into jets or cones. Then what we see is brighter than the average, not truly exceeding Eddington. Or the accretion disk geometry might be different. Thick disks, slim disks, allow higher accretion rate without blowing themselves apart. Understanding how black holes can exceed this limit helps explain how supermassive black holes grew so quickly in the early universe. They must have had periods of super Eddington growth, feeding voraciously to reach billions of solar masses in less than 1 billion years. The Eddington limit is a guideline, not a law. Nature finds ways around it, as it often does. At the center of our galaxy, stars orbit Sagittarius A star, the supermassive black hole. In tight elliptical paths, star S2 orbits every 16 years, getting as close as 120 AU, about 4 times Neptune's distance from the Sun. But near a 4 million solar mass black hole, that's incredibly close. S2 reaches 3% of light speed at its closest approach. By tracking S2 over decades, astronomers measured relativistic effects, gravitational redshift, the stretching of light, exactly as Einstein predicted. S62, another star, has an even tighter orbit, approaching to just 16 light hours, moving faster than S2. These stars are laboratories, testing general relativity in extreme conditions, strong gravity, high velocity, where Newton's laws fail. If a star ventured even closer, it might be torn apart by tidal forces, the Roche limit, where the black hole's gravity overwhelms the star's self-gravity. Some stars have been observed making their closest approach and surviving, but others wandered too close and were shredded, creating bright flares as the debris fell in. By watching these stellar orbits, we mapped the black hole's position, its mass, its influence, proving beyond doubt that it's there, even though we can't see it. The orbits themselves are beautiful, elegant, cosmic clockwork, playing out over decades and centuries, indifferent to our observation, ancient dances, continuing forever. Quasars, quasi-stellar objects, discovered in the 1960s, appeared as bright points of light, but with strange spectra. They were incredibly distant, billions of light years away, and yet shone brighter than entire galaxies. The only explanation? Supermassive black holes feeding vigorously, accretion disks glowing with the energy of trillions of stars. Quasars were most common when the universe was younger, 3 to 5 billion years after the Big Bang, a peak era of black hole feeding. Today, quasars are rarer. Most supermassive black holes have gone dormant, starved of fuel. Blazars, a type of quasar, have their jets pointed directly at Earth. We're looking down the barrel of a relativistic particle beam. This makes them appear even brighter and more variable, flaring on timescales of days or hours as clumps of plasma travel down the jet toward us at near light speed. The light is Doppler boosted, blue shifted, intensified by the motion of the jet. Relativistic beaming. Blazars helped prove that supermassive black holes exist in distant galaxies, their extreme luminosity can only be explained by accretion onto black holes. OJ287, a blazar, shows periodic outbursts every 12 years, suggesting it's a binary. Two supermassive black holes orbiting each other, the smaller one punching through the accretion disk of the larger, creating a flare each time. Quasars and blazars are windows into the early universe, showing us how galaxies formed, how black holes grew, and how they shaped the cosmos around them. Accretion disks aren't smooth. They have weather, storms, turbulence, flickering. Magnetic fields thread through the disk, tangling, reconnecting, creating hotspots that flare and fade. This is why black hole systems vary in brightness on timescales from seconds to years. The disk is constantly changing, churning, evolving. Magnetorotational instability drives turbulence in the disk. Magnetic fields amplify, creating friction, which heats the gas and allows it to spiral inward. Without this instability, accretion would be much slower. Matter would orbit stably, never falling in. Coronae, regions above and below the disk, are even hotter, millions of degrees, emitting hard X-rays. The corona's exact structure is still debated. Is it a continuous layer or isolated hotspots hovering above the disk? Flares in the corona can be triggered by magnetic reconnection, similar to solar flares, but millions of times more energetic. Disk winds blow outward, driven by radiation pressure or magnetic forces, carrying away angular momentum and allowing the remaining gas to fall inward. These winds can be detected through absorption lines in the X-ray spectrum, blue shifted by their motion toward us. State transitions when a black hole system changes behavior from a hard state dominated by corona to a soft state dominated by disk emission, or vice versa. These transitions happen as the accretion rate changes, the disk geometry shifts, and the black hole's feeding mode switches from one regime to another. Watching black hole weather teaches us about plasma physics, magnetic fields, and the behavior of matter in extreme conditions. Sagittarius A star, SCA-S, sits 26,000 light-years away at the heart of the Milky Way, 4 million solar masses compressed into a region smaller than Mercury's orbit. It's quiet now, barely feeding, emitting faint radio waves, occasional X-ray flares when gas clouds wander close. But in the past, it may have been much more active, a quasar, perhaps billions of years ago. Evidence of past activity comes from the Fermi bubbles, enormous lobes of gamma rays extending above and below the galactic plane, 50,000 light-years tall. These bubbles might have been inflated by jets from SCRI millions of years ago when it last fed heavily, or they could be from a burst of star formation in the galactic center, supernovae, stellar winds driving gas outward. Either way, The galactic center was once far more violent than it is today. In 2019, Escarre brightened by a factor of 75 for a few hours, the brightest flare ever recorded. What caused it? Perhaps a gas cloud, torn apart by tidal forces, or an asteroid, evaporated by friction as it spiraled inward. Future observations with the Event Horizon Telescope will image SGR-A, capturing its shadow, just as they did with M87A. But SGR-A is more challenging, smaller, varies faster. The image blurs as gas orbits in minutes rather than days. Still, we'll see it, our home galaxy's heart, revealed, a silent giant waiting patiently for its next meal. Sometimes a black hole has a companion, a pulsar, a rapidly spinning neutron star, emitting beams of radio waves like a cosmic lighthouse. These binary systems are rare, but incredibly useful. The pulsar acts as a clock, precisely timed, and the black hole's gravity warps the pulsar's signal. By measuring these timing variations, we can map the orbit, determine the black hole's mass, test general relativity with exquisite precision. PSR J1713 plus Rho 747, a pulsar orbiting a white dwarf, but similar systems exist with black holes instead. The gravitational waves from such systems are too weak to detect yet, but future detectors, like LISA, the Laser Interferometer Space Antenna, will hear them humming through space. When a pulsar orbits close to a black hole, its beam can sweep across us, appearing, disappearing, with clockwork regularity, sometimes milliseconds apart, the Shapiro delay. When the pulsar signal passes near the black hole, time dilation slows it down, arriving slightly late. The delay reveals the black hole's mass and position. Some systems show eclipses when the pulsar passes behind the accretion disk, its signal blocked, then emerging on the other side. Black hole pulsar binaries are natural laboratories where we can study extreme gravity, strong field effects, frame dragging, spin precession, all encoded in radio timing. Finding more of these systems is a priority, each one a treasure, revealing secrets about how gravity works in its strongest forms. When an object is deformed by tidal forces, how much it resists is described by tidal love numbers. For black holes, these numbers are zero. They don't deform at all. They're perfectly rigid, in a sense. This is because the event horizon isn't a physical surface, it's a mathematical boundary. There's nothing to stretch or squeeze. Neutron stars, by contrast, have non-zero love numbers. They deform under tidal stress, bulging slightly when stretched by a companion. During a merger of two objects, the gravitational wave signal encodes their love numbers, revealing what they're made of. When LIGO detected the neutron star merger GW17087, the signal revealed tidal deformability, confirming they were neutron stars, not black holes. If they'd been black holes, the signal would have been different. No tidal effects, just pure orbital decay and merger. Measuring love numbers helps us distinguish between black holes and other compact objects and understand the equation of state of ultra-dense matter. It's a strange name. Tidal love numbers, named after Augustus Edward Hauff-Love, a mathematician from the 1800s who studied Earth's tides. But the concept applies to all objects in strong gravity, from planets to neutron stars, and even, in a sense, to black holes, though their answer is always zero. This rigidity, this inability to deform, is another sign of the black hole's strange nature, a hole in space-time, not an object within it. Black holes inspire not just scientists, but artists, musicians, dreamers. Holst never wrote about black holes, but if he had, what would they sound like? Deep, resonant, ominous, or quiet, subtle, fading? Modern composers have tried translating gravitational wave data into sound. The chirp of merging black holes becomes a musical phrase, rising, accelerating, resolving. Visual artists depict them, swirling discs of light, darkness at the center, representing the unknown, the unknowable. Black holes appear in installations where light bends through curved mirrors or projected images, creating the illusion of warped space. They symbolize absence, void, mystery, but also power, transformation, rebirth. What falls in is destroyed, but also, in a sense, preserved. Photographers at NASA and ESO create stunning visualizations based on real data from simulations, showing what we'd see if we could visit. These aren't fantasies, they're predictions, grounded in physics, translated into imagery that captures the imagination. Poetry, too, finds black holes compelling, metaphors for loss, for grief, for the passage of time, for things that can't be undone. We project our emotions onto these cosmic objects, seeing in them reflections of ourselves, our fears, our curiosities, our awe at the universe. And perhaps that's fitting, because black holes remind us that we're part of something vast, ancient, beautiful, and terrifyingly indifferent. When light from a distant galaxy passes near a black hole, it bends, following the curve of space-time. This is gravitational lensing, and black holes are powerful lenses. Einstein predicted this in 1915, but it wasn't confirmed until a solar eclipse in 1919, when stars near the Sun appeared shifted, their light bent by the Sun's gravity. Near a black hole, the effect is far stronger. Light can wrap around multiple times, creating multiple images of the same background object. An Einstein ring forms when a black hole is perfectly aligned between us and a distant light source. The light bends into a circle, a ring of light surrounding the dark center. If the alignment isn't perfect, we see arcs or multiple images, distorted, stretched. by the gravitational lens. Microlensing occurs when a smaller black hole passes in front of a star. The star brightens temporarily as its light is focused toward us. This technique helps us search for isolated black holes drifting through space, dark, invisible, revealed only by their gravity. Strong lensing by supermassive black holes can magnify distant galaxies, making them visible when they'd otherwise be too faint. It's like nature provided a telescope built from gravity itself, bending space to show us the unreachable. The lensing also encodes information about the black hole's mass, spin, and position, all extracted from the pattern of distorted light. Every photon tells a story of its journey through curved space around invisible giants to finally reach our eyes. We're in a golden age of black hole astronomy. New detectors, new telescopes, revealing them in unprecedented detail. The Event Horizon Telescope will image more black holes, creating a gallery of event horizons, comparing sizes, shapes, spins. LISA, launching in the 2030s, will detect gravitational waves from supermassive black hole mergers across the universe, opening a new window on cosmic history. The Vera Rubin Observatories will survey the sky, finding thousands of new tidal disruption events, stellar deaths by black hole. Next-generation X-ray telescopes will study accretion disks, coronae, winds in exquisite detail, mapping the flow of matter in strong gravity. Quantum gravity experiments might one day probe the singularity itself, or at least the Planck scale, where space-time becomes grainy. Artificial intelligence is accelerating discovery, analyzing vast data sets, finding patterns humans miss, classifying black holes, predicting their behavior. Citizen science projects invite everyone to help search for black holes, classifying galaxies, identifying candidates, contributing to science. The questions we're asking now are deeper than ever. What happens at the singularity? How is information preserved? Can we unify quantum mechanics and gravity? Are black holes gateways to other universes? And with each discovery, new questions arise. The more we learn, the more we realize how much we don't know. But that's the beauty of science. The endless frontier, always another mystery beyond the horizon. Dark matter makes up 85% of all matter, but we've never detected it directly. We know it's there by its gravitational effects. What if dark matter isn't exotic particles, but primordial black holes? Tiny black holes formed in the Big Bang. They'd be invisible, emit no light, interact only through gravity, exactly like dark matter. The idea is old, proposed by Stephen Hawking and others in the 1970s, but new observations have revived interest. If primordial black holes exist in the right mass range, they could explain dark matter without needing new physics. Searchers look for microlensing events when a primordial black hole passes in front of a distant star, briefly brightening it. So far, the results are mixed. Some mass ranges are ruled out, others remain possible. Asteroid mass black holes or planet mass could still be hiding in the dark matter halo of our galaxy. LIGO's detections of merging black holes in unexpected mass ranges hint that some might be primordial. If true, it would solve two mysteries. What is dark matter, and where did these black holes come from? With one answer, but most physicists remain skeptical. The constraints are tight, and alternative explanation for dark matter are still viable. The search continues through microlensing surveys, gravitational wave detections, and observations of the early universe. Perhaps dark matter is something stranger. WIMPs, axions, sterile neutrinos, or perhaps it's been black holes all along, gamma ray bursts, the most energetic explosions since the Big Bang. They last seconds to minutes, releasing more energy than the sun will emit in its entire lifetime. Longer gamma ray bursts come from collapsing massive stars, hypernovae, where the core collapses directly to a black hole. Jets of gamma rays shoot out along the rotation axis at near light speed. If one is pointed at Earth, we see a gamma ray burst. Short gamma ray bursts come from mergers, two neutron stars, or a neutron star and black hole, colliding, forming a black hole and emitting a burst, GRB 7082-7A, accompanied the gravitational wave event, GW 170817, confirming the merger origin of short bursts. The mechanism involved the black hole and its accretion disk. Magnetic fields twist, launching jets, funneling energy outward. Within the jet, particles accelerate to relativistic speeds, colliding, producing gamma rays that we detect billions of light years away. The afterglow lasts days to weeks as the jet slows, interacting with surrounding gas, emitting X-rays, visible light, radio waves. Gamma ray bursts are beacons, allowing us to study the distant universe, the early universe when stars were just forming. They're also potential threats if one occurred within our galaxy, pointed at Earth. It could strip away the ozone layer, causing mass extinction. But such events are rare, perhaps once per galaxy, every few million years, and the odds of being in the beam are tiny. Still, they remind us the universe is dangerous, beautiful, but not benign, and black holes are at the center of some of its most violent moments. Some theories propose that our universe is one of many, a multiverse, an infinite collection. Black holes might connect to other universes through their singularities or through baby universes budding off. Lee Smolin's cosmological natural selection suggests that universes reproduce through black holes. Each black hole creates a new universe with slightly different physical constants. Universes that make more black holes have more offspring, so over time, the multiverse becomes populated by universes optimized for black hole formation. This could explain why our universe has the constants it does, values fine-tuned to allow stars, galaxies, black holes, eternal inflation. Another multiverse theory suggests that universes bubble off from each other in an ever-expanding multiverse. Each bubble has different physics, different forces, some with black holes, some without. Inside a black hole, some physicists speculate a new universe might form, expanding outward in its own space and time, disconnected from ours. To us, it's just a singularity, but from inside, it might look like a big bang. These ideas are speculative, untestable, perhaps untestable forever, but they push the boundaries of what we imagine, what's possible. Black holes, already strange enough, become even stranger as gateways, birthplaces of entire universes. Whether true or not, they expand our thinking about reality, existence, the nature of everything. When multiple objects orbit a black hole, their orbits can synchronize, falling into resonances. A 2-to-1 resonance means one object orbits twice for every orbit of another. Their gravitational tugs align periodically, reinforcing each other. These resonances affect orbital stability. Some resonances are stable, locking objects into place. Others are unstable, ejecting objects over time. Around supermassive black holes, stars can fall into resonances, creating patterns in their orbital distribution. Accretion disk instabilities might also involve resonances between different parts of the disk, creating waves, oscillations that modulate the emitted light. Quasi-periodic oscillations, QPOs, seen in X-ray light curves, might arise from resonances between orbital frequencies near the black hole. The innermost stable circular orbit, the ISCO, defines a boundary, inside which stable orbits don't exist. Matter spirals inward, inexorably. But near the ISCO, orbital dynamics become complex. Precession, frame dragging, all influence the motion. Binary black holes can have resonant interactions, affecting their merger time and the gravitational waves emitted. Resonances are everywhere in planetary systems, asteroid belts, and around black holes. They're nature's way of organizing chaos, creating structure from randomness. Understanding resonances helps us predict long-term behavior of systems around black holes. They're subtle but powerful, shaping the cosmos, one orbit at a time. Cygnus X1, a bright X-ray source discovered in the 1960s in the constellation Cygnus. It was identified as a binary system, a blue supergiant star orbiting something invisible. The invisible companion was too massive to be a neutron star, more than 3 solar masses, the Tolman-Oppenheimer-Volkoff limit. It had to be a black hole. the first one ever confirmed, Stephen Hawking famously bet against it being a black hole in 1974 with Kip Thorne. Hawking lost the bet and conceded in 1990, subscribing Thorne to a magazine. As per the terms, the black hole in Sig X1 is about 21 solar masses, accreting gas from its companion. The gas forms a disk, heating up, emitting X-rays. Sometimes the system flares as clumps of matter fall into the black hole, releasing bursts of energy. Jets have been detected shooting out from the poles at relativistic speeds, visible in radio waves. Sig X1 is only 6,000 light-years away, relatively close, allowing detailed study of its properties. Observations over decades measured its spin, nearly maximal, rotating close to the speed of light. This discovery opened the door to black hole astronomy, proving they exist, confirming Einstein's prediction, and launching a new field. Today we know of dozens of stellar mass black holes, but Sig X1 will always be special. The first, the one that changed everything. Black holes are simple, deceptively simple. They have no features, no distinguishing marks. The no-hair theorem states that black holes are completely described by just three numbers: mass, charge, and spin. Nothing else matters. Whether the black hole formed from hydrogen or iron, from stars or gas, the end result is the same. All other information is erased. This is shocking because it means black holes are generic, interchangeable, with no memory of their origin. The event horizon smooths out all irregularities, all bumps, all structure, leaving a perfectly smooth surface, or rather, a perfectly smooth mathematical boundary, since the horizon isn't a physical surface. John Wheeler coined the phrase, "Black holes have no hair," meaning no extra features beyond mass, charge, and spin. But recent research suggests there might be soft hair, quantum information stored in subtle ways at the event horizon. This wouldn't violate the classical no-hair theorem, but would allow information preservation through quantum effects. The debate continues between those who believe black holes are truly featureless and those who think quantum mechanics adds complexity. Either way, black holes are simpler than any other object in the universe, defined by almost nothing, yet containing everything. A paradox, wrapped in an event horizon. And so we continue drifting through these endless mysteries as black holes waiting patiently in the darkness of space, pulling, bending, transforming everything they touch. There's something almost peaceful about black holes, despite their power. They don't chase, they don't hunt, they simply exist, warping space around them, creating wells so deep that even light cannot climb out. Imagine standing at the edge, not falling, just observing, watching light bend around the event horizon, circling, spiraling, like water around a drain, but slower, more graceful, photons dancing their final dance before disappearing forever. The event horizon itself is not a place you could stand. It's not solid, not physical, just a boundary, a point of no return. Cross it, and all paths lead inward to the singularity where mathematics breaks and our understanding ends. But before that moment, before the final plunge, there would be beauty, the accretion disk glowing, orange and blue, heated by friction, by compression, by the inexorable pull, spinning faster, hotter, brighter as it descends. Some black holes are quiet, dormant, waiting in the dark, with no material nearby to consume. They're invisible, detectable only by their gravitational influence, tugging at nearby stars, bending light from distant galaxies, silent giants, patient, eternal. Others are violent, feeding actively, tearing apart stars that wander too close. The stellar material doesn't fall straight in. It forms a disk, and in that disk, chaos, turbulence, magnetic fields twisting and reconnecting, heating the gas to millions of degrees. The jets that shoot from some black holes, perpendicular to the disk, are among the most energetic phenomena in the universe. Particles accelerated to nearly light speed, streaming outward for thousands of light years, visible across the cosmos, beacons powered by darkness. Time near a black hole behaves strangely. An hour near the event horizon could equal years far away. This isn't science fiction. It's measured, proven. Time is flexible, malleable, shaped by gravity. If you could orbit close, just outside the photon sphere, and then return home, you'd find that everyone you knew had aged while you remained young, a one-way journey into the future, powered by extreme gravity. Inside the event horizon, our understanding falters, the singularity, where all the mass concentrates into a point infinitely small, infinitely dense, defies our equations, defies our intuition. It's where general relativity and quantum mechanics clash. Some physicists think the singularity isn't real, that quantum effects, at the smallest scales, prevent infinite density, creating instead something else, a bounce, a transition, a doorway to somewhere unknown. Black holes preserve information or destroy it, depending on which physicist you ask. This paradox, the information paradox, drives research, inspires theories, pushes us toward a deeper understanding of reality. Hawking radiation, the slow evaporation, happens over timescales so vast we can't truly comprehend them. A solar mass black hole would take longer than the current age of the universe to evaporate completely. But eventually, even black holes die. When two black holes merge, the event is cataclysmic, more energy released in a second than all the stars in the observable universe emit, combined, but not as light, as gravitational waves, ripples in space-time itself, spreading outward forever. We've detected dozens of these mergers now, each one unique, each one teaching us about mass, spin, distance, the population of black holes scattered throughout the cosmos. The shadow of a black hole, photographed for the first time in 2019, showed us what we'd only imagined: a dark circle surrounded by glowing light, exactly as predicted by Einstein's equations, written more than a century ago. That image of M87's black hole is a triumph of human curiosity, cooperation, and persistence. 8 telescopes around the world working together as one, creating a virtual telescope the size of Earth. And yet, despite all we've learned, black holes remain mysterious. They mark the edge of our knowledge, the boundary between the known and the unknowable, places where the universe keeps its deepest secrets. They remind us that reality is stranger than we imagine, that our intuitions fail at the extremes, that there are things we can describe mathematically but never truly understand emotionally, experientially. Black holes are teachers, showing us humility, showing us wonder, showing us that the universe doesn't owe us comprehension. It simply is vast, beautiful, indifferent, and we, tiny, brief, get to witness it for a moment. As you drift deeper now into sleep, let these thoughts dissolve like stars into darkness, black holes waiting patiently in the vast expanse, bending space, bending time, bending light while you rest, safe, far away, held by gravity of a different kind, the gentle pull of sleep drawing you down, down into dreams. And so we continue drifting through these endless mysteries, black holes waiting patiently in the darkness of space, pulling, bending, transforming everything they touch. There's something almost peaceful about black holes. Despite their power, they don't chase, they don't hunt, they simply exist, warping space around them, creating wells so deep that even light cannot climb out. Imagine standing at the edge, not falling, just observing, watching light bend around the event horizon, circling, spiraling, like water around a drain, but slower, more graceful. Photons dancing their final dance before disappearing forever. The event horizon itself is not a place you could stand. It's not solid, not physical, just a boundary, a point of no return. Cross it, and all paths lead inward to the singularity, where mathematics breaks and our understanding ends. But before that moment, before the final plunge, there would be beauty, the accretion disk glowing, orange and blue, heated by friction, by compression, by the inexorable pull, spinning faster, hotter, brighter as it descends. Some black holes are quiet, dormant, waiting in the dark, with no material nearby to consume. They're invisible, detectable only by their gravitational influence, tugging at nearby stars, bending light from distant galaxies, silent giants, patient, eternal. Others are violent, feeding actively, tearing apart stars that wander too close. The stellar material doesn't fall straight in, it forms a disk, and in that disk, chaos, turbulence, magnetic fields twisting and reconnecting, heating the gas to millions of degrees. The jets that shoot from some black holes, perpendicular to the disk, are among the most energetic phenomena in the universe. Particles accelerated to nearly light speed, streaming outward for thousands of light years, visible across the cosmos, beacons powered by darkness. Time near a black hole behaves strangely. An hour near the event horizon could equal years far away. This isn't science fiction, it's measured, proven. Time is flexible, malleable, shaped by gravity. If you could orbit close just outside the photon sphere and then return home, you'd find that everyone you knew had aged while you remained young. A one-way journey into the future, powered by extreme gravity. Inside the event horizon, our understanding falters. The singularity, where all the mass concentrates into a point infinitely small, infinitely dense, defies our equations, defies our intuition. It's where general relativity and quantum mechanics clash. Some physicists think the singularity isn't real, that quantum effects at the smallest scales prevent infinite density, creating instead something else, a bounce, a transition, a doorway to somewhere unknown. Black holes preserve information or destroy it, depending on which physicist you ask. This paradox, the information paradox, drives research, inspires theories, pushes us toward a deeper understanding of reality. Hawking radiation, the slow evaporation, happens over timescales so vast we can't truly comprehend them. A solar mass black hole would take longer than the current age of the universe to evaporate completely. But eventually, even black holes die. When two black holes merge, the event is cataclysmic, more energy released in a second than all the stars in the observable universe emit, combined, but not as light as gravitational waves, ripples in space-time itself, spreading outward forever. We've detected dozens of these mergers now, each one unique, each one teaching us about mass, spin, distance, the population of black holes scattered throughout the cosmos. The shadow of a black hole, photographed for the first time in 2019, showed us what we'd only imagined: a dark circle surrounded by glowing light, exactly as predicted by Einstein's equations, written more than a century ago. That image of M87's black hole is a triumph of human curiosity, cooperation, and persistence. 8 telescopes around the world working together as one, creating a virtual telescope the size of Earth. And yet, despite all we've learned, black holes remain mysterious. They mark the edge of our knowledge, the boundary between the known and the unknowable, places where the universe keeps its deepest secrets. They remind us that reality is stranger than we imagine, that our intuitions fail at the extremes, that there are things we can describe mathematically, but never truly understand emotionally, experientially. Black holes are teachers, showing us humility, showing us wonder, showing us that the universe doesn't owe us comprehension. It simply is vast, beautiful, indifferent, and we, tiny, brief, get to witness it for a moment. As you drift deeper now into sleep, let these thoughts dissolve like stars into darkness, black holes waiting patiently in the vast expanse, bending space, bending time, bending light, while you rest, safe, far away, held by gravity of a different kind, the gentle pull of sleep drawing you down, down into dreams. Deeper still, we venture into the hearts of galaxies where supermassive black holes dwell, millions, billions of times the mass of our sun, anchoring entire cosmic cities, stars orbiting them, like planets around a star, but on scales immense, incomprehensible. Sagittarius A, at the center of our Milky Way, a quiet giant, 4 million solar masses, compact, lurking, revealed through the dance of nearby stars, whipping around at incredible speeds, their paths tracing the invisible mass, a shadow we imaged in 2022, another dark circle, ringed in fire, proof that even our home galaxy harbors such a beast. These supermassive ones, how do they form? Some from mergers, black holes colliding, growing over billions of years. Others perhaps from direct collapse, massive gas clouds imploding under their own weight in the early universe, when everything was denser, hotter, more chaotic. Intermediate black holes, the missing links between stellar and supermassive, elusive, hidden in globular clusters, or the remnants of ancient mergers. We've glimpsed a few through gravitational waves or X-ray bursts, hints of a population bridging the gaps. The no-hair theorem whispers simplicity, a black hole defined by just 3 things: mass, charge, spin, no other details, no history etched on its surface, all complexity erased, reduced to basics, like a cosmic reset button pressed by gravity. But spin matters. Kerr black holes, rotating, frame-dragging space-time, twisting it like a vortex. Ergospheres where you could hover, extracting energy. The Penrose process, stealing rotational power, turning black holes into engines, hypothetical yet mathematically sound. Primordial black holes, born in the Big Bang's aftermath, tiny, perhaps microscopic, evaporating quickly or lingering as dark matter candidates, explaining the unseen mass, holding galaxies together, invisible threads woven into the fabric of the cosmos. The holographic principle, inspired by black holes, suggests our 3-dimensional reality is a projection from a 2-dimensional surface, like the event horizon, information encoded there, never lost, challenging our sense of depth, of volume, making the universe a grand illusion. Quantum entanglement and black holes intertwined, Some theories propose wormholes as bridges, ER equals EPR, connecting distant points through quantum links, black holes as portals, not to other universes, but to entangled partners, a network beneath reality. Recent gazes from the James Webb Space Telescope, peering back in time, spotting black holes in the dawn of the universe, surprisingly massive, grown too fast, challenging models, forcing us to rethink seeding, growth, the early cosmos more fertile than we knew, black holes in binaries, dancing with companions, neutron stars, or other black holes, their orbits decaying, spiraling inward until merger, the final chirp, detected by LIGO, Virgo, Kagra, waves washing over Earth. From billions of light years away, each detection a story of violence, creation, evolution, entropy of black holes, vast, proportional to surface area, not volume. Bekenstein-Hawking formula linking gravity to thermodynamics, treating horizons as hot, radiating, a bridge between classical dust and quantum worlds, entropy as information, hidden but countable. In fiction, black holes devour ships, warp time for heroes, but reality is subtler. No sudden sucks, just gradual pulls, spaghettification, stretching you thin as tides tear atoms apart, long before the horizon, a gentle end from afar, horrific up close, yet some speculate. Traversable wormholes, stabilized by exotic matter, connecting through black holes, shortcuts across space or time, dreams of travel, balanced on the edge of possibility and paradox. As we learn more from simulations, supercomputers crunching equations, modeling in falls, jets, mergers, revealing dynamics we couldn't observe directly, virtual universes mirroring the real, teaching us patience, precision. And in 2025, new detections roll in. Gravitational wave observatories expanding, space-based like LISA, listening for lower frequencies, supermassive mergers, the bass notes of the cosmic symphony, rumbling through space-time. Black holes challenge us to unite theories, quantum gravity, strings, loops, holograms, paths to a theory of everything, where singularities smooth out, infinities tamed, reality revealed in full. They embody duality, destroyers, creators, seeding galaxies, regulating star formation, their feedback loops, quenching, igniting, cosmic balance keepers, drifting further. Let these enigmas fade into the night, black holes eternal, patient as you surrender to rest, thoughts evaporating like Hawking's glow, slow, inevitable, into peaceful void. Black holes remind us that the universe is stranger than we imagine, that our intuitions fail at the extremes. They are the ultimate unknown, places where knowledge ends and mystery begins. Einstein initially didn't believe they could exist. He thought the universe would find a way to prevent such extreme objects. But nature is more creative than we are. And black holes, impossible as they seem, are real. They teach us humility, that there are things we cannot see, cannot reach, cannot fully understand, and that's okay. The universe doesn't owe us answers. It simply is, vast, beautiful, indifferent, and we, tiny, brief, get to witness it for a moment. Black holes are the universe's secret keepers, holding information, energy, matter, in a place we can never retrieve it from. The ultimate vault, locked forever. And yet, we study them, we photograph them, we detect their mergers, we calculate their properties, we dream about them, because that's what we do. We explore, we question, we wonder. Even knowing we'll never have all the answers, we still reach out into the dark, searching for light, for meaning, for connection. And so we drift through these 100 mysteries, gentle wonders, looping softly, endlessly. Black holes, silent and strange, waiting at the edges of comprehension, bending time, bending space, bending light. But here, now, you are safe, far from event horizons, far from singularities, just resting, breathing, floating. Let these thoughts dissolve like stars into darkness, each one fading softly until only sleep remains. Your body is heavy now, sinking deeper into comfort, every muscle releasing, every breath slower, softer. The universe is vast, but you're here, small, safe, held by gravity, by warmth, by rest. Thump, 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 your heartbeat, steady, slow, matching the quiet rhythm of space. Nothing to do, nowhere to go, just this moment, this breath, this calm. And if your mind wanders back to black holes, let it. Let the thoughts float through, like light passing near an event horizon, bending, dimming, drifting away. You don't need to understand. You don't need to remember. You just need to rest. And the mysteries will still be here when you wake, waiting patiently in the dark. The universe keeps turning. Black holes keep pulling.